Hello everyone, today I will present my software project called Smart CO2 Controller for Recirculating Aquaculture Systems, or RAS. This system was developed to automatically monitor and control dissolved CO2 levels in aquaculture water. Maintaining safe CO2 levels is important because excessive CO2 can stress fish, reduce growth, and increase mortality. This activity diagram shows the workflow of the Smart CO2 Controller software. First, the system reads sensor data from pH, temperature, and salinity sensors. Next, the readings are validated to ensure they are reliable. The operator then sets or the system retrieves the latest alkalinity value, which is required for CO2 prediction. Using the sensor data and alkalinity, the software calculates dissolved CO2 concentration. The calculated CO2 is compared with the target set point. If CO2 is too high, aeration is increased. If CO2 is low, aeration is decreased to save energy. The control signal is sent to the VFD to adjust fan speed. Finally, the system stores data and updates charts for monitoring. This cycle repeats continuously to maintain safe water quality for fish. The software was designed using unified process and UML modeling. The use case diagram here shows the main use cases of the software and the main artists. The class diagram shows the main software modules. The main responsible module is the CO2 controller. The system sequence diagram shows how all actors interact with the CO2 controller system. The interaction diagram shows how these components interact during real-time operation. This design improves maintainability and modularity. The software has the following features. 1. Configuration. The operator enters model parameters, PI parameters, CO2 set point, sampling time, alkalinity value, and safe alarm limit, and the configuration settings are then validated. 2. Sensor acquisition. The system continuously reads temperature, pH, and salinity values from RAS sensors and validates values. 3. CO2 predictions. Using the predictive carbonate chemistry equation, the software estimates dissolved CO2 concentration in real time. 4. Automatic control. The estimated CO2 is compared with the target set point. A PI controller calculates the actuator's output. The output signal adjusts the VFD degasser speed to remove excess CO2. 5. Safety features. If sensor values fail or CO2 exceeds critical limit, alarms are raised. Fallback operation is activated and maximum aeration can be forced. 6. Data logging. All sensor values, estimated CO2, and VFD speed are stored in the database for future analysis, and the cycle is repeated. Here is a developed first version front panel of the software developed in LabVIEW. The operator can set CO2 target, view current process CO2, average CO2, degasser speed in Hz, temperature, pH, salinity, and set alkalinity. The operator can also change process model and PI parameters, sample time, or stop the system. The trend graph displays both CO2 concentration and VFD fan speed. It is also expected that degassing speed will reduce when higher CO2 levels are preferred. Alarm indication is shown on the front panel to alert the operator when CO2 is above critical limit. This allows operators to monitor system response in real time. The block diagram in lab view shows the implementation logic connecting sensors, predictive model, PI controller, alarms, and database functions for future analysis. Data stored in the database can be queried for analysis. In conclusion, this smart CO2 controller provides an intelligent and low-cost solution for modern aquaculture systems. It replaces expensive direct CO2 sensors with predictive modeling and automatic control. The system improves fish welfare, reduces operator workload, saves energy, and supports smart aquaculture management. Thank you for your time.